Our design uses the principles of Pascal's law, which states that the pressure exerted anywhere in a contained incompressible fluid is equally distributed in all directions throughout the fluid. As the driver applies a force on the brake, the same force is distributed to the pressurized fluid. The force is then amplified by increasing the contact area near the brake pad. This force provided from the driver allows the first brake pad to come in contact with the rotor. As the first brake pad comes in contact with the rotor, the equal and opposite force exerted by the rotor is then transferred to the caliper frame, transitioning the system in order for the second brake pad to come in contact with the rotor. The frictional force provided by both brake pads decelerates the rotor, allowing the vehicle to stop on demand.
Our design contains of several parts that are essential to building the product. Most parts are made of cold-drawn steel, such as the rotor, frame, screws, brake pad, and the connecting rods. The rotor has a diameter of 290 millimeters and is 50 millimeters high, with a mass of 6 kilograms. The frame has a length of 252 millimeters, 100 millimeter width, and 100 millimeter height, with a mass of 2 kilograms. The screws have an 8 millimeter diameter and a weight of 4 grams. The brake pad has a length of 120 millimeters, width of 60 millimeters, 20 millimeters high, and a weight of 621 grams. Connecting rods have a diameter of 3.25 millimeters and a mass of 6 grams. Cold-drawn steel was chosen for its high yield strength for when the friction process occurs. Another part, such as the rubber bellows, are made of rubber and have a diameter of 24 millimeters, height of 40 millimeters, and a mass of 10 grams. Aluminum is also a material we use for two parts, the piston and cylinder. The piston has a diameter of 80 millimeters and is 25 millimeters high. The cylinder has a diameter of 70 millimeters and is 100 millimeters high.
When doing our FEM analysis, we looked at the main stresses on our design. This would be a force of 2.7 kilonewtons on each brake pad and also the heat due to the friction of the rotor and brake pad rubbing together. We specifically looked at the brake pads, the screws, the shells, and the rotor. In our design, we figured that the most at-risk parts would be the brake pad and the screws, as they might be the weakest part of our design and that it would take the most force. Doing our analysis, it showed that the brake pad would only deform by 0.001 millimeters. We have a very similar situation with the screws. They only deform slightly as well. In conclusion, the screws and the brake pads would be able to successfully take the loading conditions. Next, we did our fatigue analysis. Although the pads and screws were able to take the stresses in one instant, we needed to test that they could last a long time, ideally an infinite life. When we did the fatigue analysis, all the components except the screws gave us results that there would be no fatigue in the infinite cycles. For the screws, the test showed that a very small part beneath the head of the screw would have some fatigue after a million cycles. Although it was a very small fatigue, it still jeopardizes the safety of our design. To combat this, we can make the design of the screw shorter so that the body can withstand more stress, or we can do a routine checkup to replace the screws every now and then. Overall, the factor of safety of the entire structure ranged from 1.6 to 978, proving that the design will be safe. Alright, now we'll be doing our improvement section. Our design features a few improvements that help it perform optimally. One of these includes small holes in the rotor that are placed in a concentric manner. The holes increase heat ejection by increasing the surface area for convection to occur between the air and the material. Another improvement we made was to the caliper frame. We made it thicker in order to withstand more stresses. By doubling the thickness of it, we found that it had a much safer outcome and overall increased the factor of safety. The last improvement we made was to directly attach the brake pads to the caliper frame without the use of the caliper bracket, as it would add unnecessary risks to our design.
Once the design was finished, we ranked our design objectives based on the criteria that we initially arranged to complete. We originally set out for our design to be effective, efficient, safe, inexpensive, and aesthetically pleasing, with an emphasis on safety and effectiveness. We accomplished these objectives by increasing the amount of material we used on selective parts relative to other on-the-market products.